In a shocking development, it's time for electricity and magnetism. This video, again, has been brought to you by World's Finest Physics. We're having a summer institute for 4 days in July in Frisco, Texas, and we're not going to do any electricity and magnetism, but if we do well at this one, we might offer Physics 2 and electricity and magnetism combined sessions in the future. So if you're interested, reach out to me. Go to findphysics.com. All right, so electricity and magnetism. All right, what do we got going on here? Looks like a rotten egg is what we got going on here. All right. Non-conducting sphere, uniform volume charge density is surrounded by a thin shell, cutout view, negative Q, positive 3Q, negative Q, positive 3Q is what I want to put there. The radii of the inner and outer is okay, R4R, which you see there, okay. Determine the charge on the outer surface of the shell. Okay, so the outer surface always has the same charge as the net of everything within it. So because I see a negative Q and a positive 3, the outer surface is going to be a positive 2Q. So if you want to know, let's say that Q is 8, let's just say. So I'm going to have negative 1, 2, 3, 4, 5, 6, 7, 8. That's negative 8, negative Q. The inner surface will have exactly the same, but the opposite sign. So because the inner surface is looking at negative Q, the inner surface will have positive Q, the exact opposite of the charge it's facing. Now, the outer surface is going to have the net of all this crap. So it's going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And notice that the 1Q and the 2Q add up to the 3Q. So the 1Q, because he's facing negative 1Q, the 2Q because it's a net of 2Q inside. All right, that's how I teach my kids. Uses Gauss's law, derive an expression for electric field, distance R when you're inside. Wait a minute, did it say it's it is non-conducting. Okay, so I got to be all like integral E dot dA vector equals Q enclosed over epsilon. I don't think you honestly care if you put the vectors on it, but whatever. This is a sphere, E times 4 pi r squared. The integral side is the joke. The Q enclosed side is always the bitch. So let's have a look here. I'm going to say that the ratio Q enclosed over volume enclosed, please, it said it was uniformly dense. Yes, uniform volume charge density. Uniformly dense means that Q enclosed over volume enclosed equals Q total over volume total. So what I'm going to do is I'm going to say that Q enclosed over volume. What's the volume that's enclosed? You know, when I enclose like that little r right there, then it's going to be 4/3 pi little r cubed, Q over 4/3 pi big R cubed. Get rid of the constants, and then you get this a negative. I don't know if anybody honestly gives a shit about the negative. Okay, so let's see. Let's plop that sucker right down here. All right, and then this crap cancels out, and you get E equals negative Q times R over 4 pi epsilon naught big R cubed, negative for direction. Okay, the magnitude of the electric field exactly at R, okay, so exactly here is 8. What about at 2R? Okay, well, I'm going to say this. I'm going to say that in this between region, in between, the electric field is going to be of the form KQ over R squared. So if R doubles, then electric field is 1/4 as much, also known as 2 newtons per coulomb. Is it really this easy? That was not necessarily easy, but I don't know. Okay. Again, it might be easy, but they're trying to make it look confusing. All right, derive an expression for the absolute value of the potential difference between the outer surface of the sphere and the inner surface of the shell. Okay, well, that's just, volts equals integral E dot dr, and the electric field just KQ over R squared. I know that there's some negatives in here, but shut up. That's my response to you. All right, so it's KQ R to the negative 2 dr. I need some limits. I need a lot of limits in my life. Okay, is it R3R there? Yes, the 4R. 4. Oh, is it really 4? Yes, it is. Okay, just got to triple check. All right. So I get raise the power, divide by the new power. That we're going to evaluate that at the R to the 4R. Okay, so what happens if I do that? Then I'm going to get, oh, yeah, okay. I'm going to get KQ over R, and I'll get 1 over 1 minus 1 over 4 when you plug all that crap in. So that's 4. That's 3KQ over 4R. That's your potential difference. All right. Okay. Electric field, huh? Well, am I? Does it? It doesn't specify anything about direction. It doesn't say that outward field is. I don't know. Okay, well, I'm just going to pretend. I'm going to say positive field is directed outward. It doesn't actually say that. So there's that negative charge. Where's that egg? Okay, that's a negative. So I'm going to have, and it's linear. Okay, so linear, and then it's going to be a KQ over R squared, bitch. Okay. I don't think that was supposed to reach the axis. All right, well, and when you get outside, it's now positive electric field pointing away from the positives. And it's going to be the 1 over R squared again, but it's going to like leap up kind of like that or something. All right. Okay, I'm gonna work my way in this time. So electric potential. So electric potential at infinity is 0. As I go toward this positive electric field, that positive electric field is going to build up positive electric potential like that, maybe. Now this negative electric field is going to build up negative electric potential, and that can be discontinuous. That can be non-differentiable. That cannot be differentiable. It can't be discontinuous. It's got to be continuous. Okay, the electric field is the slope of electric potential, but negative. So negative electric field means I have a positive electric potential slope. And because that's a big negative electric field, that's a very positive slope. Now, I need a positive slope on my potential because E is dV dr with the negative. But I can't be discontinuous, and the slope needs to go towards 0. So I don't even know how to explain that, frankly. Okay, maybe you shouldn't come to my session over the summer. I can't even explain my freaking electric potential graph. All I'm thinking is 0 electric field, 0 slope. Negative electric field, positive slope. The bigger the electric field, the bigger the slope. Now the electric field goes to 0, so the slope goes to 0. Now the electric field is positive, so the slope is negative and also going towards 0. Slope and acid. Okay, let's do the set 2 of this. All right, it's a cylinder. Oh, it's pretty much the same damn problem. Do I even need to read this? Determine the charge on the outer surface of the cylindrical shell within length. I guess I do have to actually read it. What do you know? Okay, non-conducting cylinder. Of course, why would that ever be conducting? Conducting shell. Okay, so in this piece, has a net charge Q and positive 4Q, and they have R and 3R respectively. Okay, so then what was it that we were asking? Determine the charge on the outer cylindrical shell within length L. Oh, okay. Well, let's see. So if this is Q, net is positive, and this is positive 4Q net, then the outside surface would be positive Q. The inside surface would be negative Q because the inside surface has to be the exact opposite of whatever it's facing. Then the outside is going to be the net of everything. So that'd be positive 5Q. It's positive 5Q. So determine just means give me the freaking answer, positive 5Q. So determine means you don't have to show any work. So I'm not going to explain it. So eat me. All right. Gauss's law. Okay. So It's we're inside, so I'm going to fig. Okay, so an integral E dot dA equals a Q enclosed over epsilon naught. That's E times 2 pi R L. What am I going to put in for Q enclosed? Got to figure that out. All right, the Q enclosed over the volume enclosed is the Q total over the volume total. Pi R squared L and pi big R squared L. So screw you pi and screw you L. Q enclosed equals Q little r over big R. Sure. Why not? About as makes much sense as anything else I've done today. Okay, so I'm gonna have some partial cancellation. Oh yeah, is L given? Yeah, L is given. Okay, so QR over 2 pi epsilon naught L big R squared. Sure, why the hell not? Okay, the magnitude of the electric field is that. Calculate the electric field at 2R. Okay, so if you want, you would have to show this using Gauss's law again. So for cylinder, the electric field has the form, E equals C over R, where C is a constant. Okay, I'll just show it to you. Okay, so integral E dot dA equals Q enclosed over epsilon naught. In this case, it would be E times 2 pi RL equals the whole Q, because now I'm taking in this whole thing, right? Okay, over epsilon naught, right? So the E would be constant over constant, constant R. Okay, so E over CR. So double the R, half the electric field. So that's 6 newtons per coulomb. It says calculate, so you need to show some work. Hey, derive. All right, so the potential difference, okay, well, we've done this before, integral E dot dr. Now it's going to be integral this Q over 2 pi L epsilon naught. Oh, just shut up. Just bring the integral. This is right that. That is a dr. Okay, and then limits. Know your limits. No limit soldier. Here we go. R3R. Okay, that's natural log. I'm not going to show it to you. Okay, add a comment to the video if you're like, show me where that natural log 3 comes from, and maybe I'll record another video and I'll yell some more. How am I going to do this? Okay, so the electric field. I'm shuffling through my papers here like I'm trying to do my taxes. Okay, the electric field inside is positive, pointing outward, okay, and it's going to be directly proportional to R, so that's a line. Then you get this inverse reciprocal bull crap inside, so careful reciprocal function. Then when you get outside, you basically switch the Q to 5 Qs once you get outside, because the grand total charge, there's the paper that says the grand total charge. The grand total charge is 5 Qs on this entire SOB. So it's going to jump up, ideally to 5 times this height, but I'm not going to do that right now. And then it's going to reciprocal down again. Okay. So the potential is going to come in for asymptotically having reached zero. Because this is a positive electric field, this is going to be a negative slope. As the electric field gets bigger, the slope gets bigger. But now the electric field jumps down, so the slope is going to jump down again. But now the electric field goes up, so the steepness of the slope goes up. And then the electric field goes down, so the steepness of the slope goes down. Man, I probably should have planned this SOB out more than I did. All right, well, screw you, problem. All right, back to set 1. What the heck? Okay. The plates, a certain capacitor, adjustable area. That's glorious. Experiments performed to study the potential difference caused capacitor discharge to resistor. Circuit is constructed with the following equipment. Blah 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 blah. Bull crap. Okay. Draw a schematic diagram of a circuit that can charge the capacitor and may also be used to study the potential difference as the capacitor discharges. So, is there any reason why I can't just do this? So, battery. How about the switch goes here, and then let's put our variable capacitor there. Okay, somebody stabbed him with an arrow or something. And then resistor, and then maybe like voltmeter. So if you close the switch, the capacitor charges. If you open the switch, the capacitor can discharge across that there resistor. Now, how many of you are going to have your students do this? Okay. I wonder if this is technically a correct diagram. That's technically correct. Now, if I'm reading this question and I see this, I'm going to fly out to wherever your student lives and kick him in the balls. Okay, let's see. The capacitor is fully charged by the battery, discharging. Show the potential difference. Cross resistor is that. Okay, so you're supposed to start with a loop rule. So you're supposed to say like negative IR minus Q over C equals 0. Remember, when it's discharging, there's no battery, so there's not a positive EMF. Technically, the capacitor acts like the battery, but the current is also negative because the current is dq dt. So because the charge on the capacitor is decreasing, that makes this negative, which makes the opposite of a negative a positive, and that all adds to 0. So then I'm going to say, how about dq dt times r is equal to negative q over c. So then I'm going to say dq over q is negative 1 over rc dt. So I'm going to plop an integral there. I'm going to get natural log q equals negative dt over rc. Okay. And then, t plus, I can't use a c for a constant, plus k. All right. It's going to be like constant. Yeah, we are going to be German today. Yeah. So we have the constant here. And then we're going to eat up the both sides. Yeah. Okay. We eat up the both sides. And we figure out how the fuck to turn this into voltage. Well, if we multiply both sides by the capacitance, divide both sides by the capacitance, then we get the voltage. So that's going to be the delta V on the capacitor. And then, let's see, then V is equal to V naught. V is equal to V naught at times equals 0. So then we get V naught e to the minus D over RC. All right, QED. Okay, well, this is nice. I had my students do something like this. They built their own capacitors out of soda bottles, and then they did something like this with the Logger Pro. Now they had to take data over the course of like 10,000ths of a second. Who builds a capacitor that can discharge over? I mean, we use million ohm resistors, and it still takes a 10,000th of a second to discharge. This absolutely has to start at the origin. And the reason why is because you start at V naught. And so these two things are equal at the beginning, and the natural log of 1 is 0. So you absolutely got to go through through that axis right there, through that origin, I mean. All right, using the best fit line, calculate a value for the known capacitance. What the hell did I just prove? I just proved this. So if I say delta VC over delta V naught is equal to E minus T over IC. So then natural log of delta VC over delta V naught is going to equal 1 over RC negative times T. So that, let's change colors here. This is the X. This is the Y. That is the slope, which is negative. So the slope is negative 1 over RC. What is the slope of this anyway? Gosh, okay, I can't count. 0.7 is 76. Maybe 0.78 over 0.6. Does anybody know what that is? 0.78 divided by 0.6. All right, hey, that's a nice number. It's not going to be nice for long. Okay, so slope is going to be 0.7. It's technically negative minus 0 over 0.6 minus 0, which is negative 1.3. So then I'm going to go back here. I'm going to say negative 1.3 is equal to 1 over R. Oh, which we have an R, 150,000. Okay, times the C. So we're just going to cross multiply here. That's a negative. So screw both negatives, and we're going to say 1 over 150,000 times 1.3. Okay, so 150,000 times 1.3, and then reciprocate the whole thing, and the capacitance is 5.12 times 10 to the negative 6 farads. When my students do this, they get like 10 to the negative 10 farads. They might get 10 to the negative 9 if they did a really good job making their capacitor sort of model. Okay, the capacitor is adjusted so the surface area of the plates is increased. The experiment's repeated with the slope of the best fit line. Okay, so C epsilon naught A over D, more area, more capacitance. The slope was 1 over RC, so more C, less steep slope. And whoever wrote this, thank you for saying more steep, less steeper, and change instead of increases, decrease remains the same, because a lot of students struggle with things that are negative. Like an increase is actually less steep when you're negative. The AP calculus people have to deal with that. I'm glad you didn't make my physics students deal with that because they're dumb. Okay, so the ideal battery is replaced with non-ideal battery with internal resistance R. The experiment is repeated. Would the slope of the graph do anything? No. Just by answer. The data singular to me, shut up. Okay, was taken when the battery wasn't even in the circuit. So do whatever you want to it. Would the vertical intercept? No, because the intercept has to be 0 since delta VC equals delta V naught at time equals 0, and natural log of 1 is 0. I mean, okay, also, I'll even say that also the delta V naught isn't changed. Why? Because it is determined by the EMF of the battery, not the internal resistance. All right, where's the other version of this? Where'd the other version of this go? Oh, here it is. All right. So, set 2. A non-ideal capacitor has internal resistance that can be modeled as an ideal capacitor in series with a small resistor RC. Actually, you're wrong. It turns out a non-ideal capacitor would act like a capacitor with a resistance in parallel. Take it from somebody who has an electrical engineering degree. I would know. So it would actually have the resistor. And I guess we got to deal with it the way we got it, right? Okay. Students performs an experiment to determine the internal resistance of a capacitor. The circuit is to be constructed with the following available equipment. That can charge the capacitor and may also be used to study the current of the capacitor as it's the same thing. Okay, it's the same as switch. All right, here's your non-ideal capacitor. I guess I got to put the ammeter in series then. All right, well, good for me. Okay, so capacitor's fully charged. It's the same thing. So what am I going to say now? I'm going to say negative Q over C minus I, the big R, which is U. Do I have to make these variable? Okay, minus I little r. So I've got 3 voltage drops, although this one is actually going to act like a driving voltage right there. Okay, so let's group Q over C, I, R plus R. Go figure, they're in series, so you can add them like a normal person. And let's separate them. Q over C. You can tell I'm chomping at the bit to make this differential equation. dq dt, R plus R. So just added that over and made the I dq dt. So now I'm getting, let's see, dq over Q equals negative 1 over the 2 R's added, C dt. Okay, I'm not going to show this. Okay, it's the same thing as before. Do you really need to see it again? Okay, let's see. Why make a second set when anyway, why would you make a second set when it's pretty much identical? This should not go through the origin. This one should not go through the origin. Because I told you, I'm doing this cold, by the way, in case you haven't noticed. That's why I'm but I did take a gander at them as they were coming out of the copy machine, right? Because I don't know about you, but our copy machine takes like 10 seconds per page. So I can read it as it comes out. So somehow, through some kind of magical technology, these kids can just straight up get the time constant, and they grab the time constant as a function of R. Well, here's the deal. Let me give you a preview. The time constant is just going to be big R plus little r times C. Okay, so I'm going to say the time constant is big R times C plus little r times C. Now, if the tau is the Y and the big R is the X, yeah, okay, then the C is going to be the slope, and all this is going to be the intercept. So this better have an intercept. So I will not endeavor to prevent it from having an intercept. But I do want to have about the same number of dots above and below. Okay. Draw best fit line. Use the best fit line to calculate the value for the internal resistance. Okay. So what did we just say? We said tau was big RC plus little RC. Okay. So this is the Y. This is the oh wow. Okay. This is going to be tricky. This is the X. This is the slope, and then this whole thing is the intercept. Okay. So I actually have to get the slope first. So I'm going to get the slope. I'm not going to enjoy it at all. What's a decent rise for what I'm doing here? There's no other crossover points that are really pretty. Eh, okay. Well, how about 0.7, 0.67 and 0.1, so 0.57. So 0.57 over 0.3. That could maybe be a nice number. Is that number going to be pretty for old Mr. Frensley here? Yes, 0.19. It's not going to be pretty for long. So that's the slope, and that's the capacitance. So now the intercept, which is 0.1, equals RC. 0.1 is going to equal R times 0.19. So the R is going to be 0.1 over 0.19. Who came up with this problem? Sweet. Okay. So 0.53 ohms. All right. The ammeter is found to be non-ideal, which means it has some internal resistance. Is the actual value for the internal resistance for the capacitor greater, less than, or equal to the experimental internal resistance? Okay, how did I draw this again? So now the ammeter adds to the equivalent resistance. So I'm going to say this. I'm going to say that tau is equal to R equivalent C, where R equivalent is the R, the other R, and the R of the ammeter. Okay, so I'm going to say this. I'm going to say if tau is what it is, in other words, it didn't get affected anyway, then if R ammeter is greater than 0, then RC must be less to compensate. So if this is more than 0, then that's just less than what it was before, less than. Okay, the values of the variable resistor in the original experiment range from that. The experiment's repeated with the values ranging from that. Would the slope, no, be the same because the slope is the capacitance. That's a whole. Okay, so there you go. The slope's the capacitance. That didn't change. All right, now for the magnetism question, back to set 1. Okay, so what is the direction, if any, of the magnetic field? What the hell's going on even? Okay, light bulb. Okay, that's going to be important right there. Is there any tricks to this? This is just a normal current. I should probably read it, but I'm getting really impatient right now, and you probably are too. I'm surprised you're even still watching. Okay, what is the direction, if anything? If you're still watching, comment like duck feathers in the comments or something like that, so you know that you made it this far. Okay, so here you go. Just type in duck feathers and see if anybody's like, "What the hell are you talking about?" Anyway, so there you go. What's the direction of the magnetic field produced by the induced current in the rectangular loop as the current in the long wire changes direction? I hate this so much. I hate Lenz's law. Okay, so I got to grab onto the current. You got to grab on nice and hard, okay? Like, just really grip it, okay? And you'll notice that you've got some dots coming out up here. X, 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 X. It's going to start getting really X, 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 X here coming up. Just you wait. All right, so and what are we doing? Is this decreasing with time? So the end of the into the page magnetic field is decreasing. So the loop creates its own into the page field. Oh, shoot. Out of the page, I meant to say. Out of the page, magnetic, its own out of the page field to oppose this change. Okay. Calculate the magnetic flux of the loop. No, I don't want to. Okay. At time t equals 3 seconds. So flux integral b dot dA. All right. So I got to split it into tiny pieces. So here's going to be one of the pieces right here. It's got a little tiny dr. It's got a length L. Okay, so this is going to be L dr. The B is going to be the familiar mu naught I over 2 pi r. Okay, and I'm going to integrate from 1 to 3. All right, 1 centimeter to 3 centimeters. So now I have to pull out, oh, shit. Mu naught comes out. 2 pi comes out. L comes out. Let's see. Clay Aiken comes out. I mean, what do you want from me? This is dr over r. I still have these limits. Oh, no, there's the I. Oh, the I comes out because it's constant in R. It's constant in R, so I can worry about the I later. I'm not integrating with respect to time. Okay, there's 3 centimeters. So this is going to become natural log of 3. Please don't make me explain that to you. Okay, so mu naught. I think I'm expected to actually get a number. 4 pi times 10 to the negative 7. The I is, can we write it like normal people, please? 10 minus 2t. So that's 4. Yeah, okay. Yeah, sure. 4L, 0.04, all over 2 pi. Yeah. Oh, natural log 3. Okay. Well, that's just a number for this. 2e negative 7. That's mu naught over 2 pi times 4 times 0.04 times the natural log of 3. Okay. The flux is 3.52 times 10 to the negative 8 Webers. Okay, calculate the current. You know what? I don't want to. Okay, do I really have to? Okay, so the flux would have been mu naught, and I now have to make it a variable now. 10 minus 2t times the L all over 2 pi times the natural log of 3. So the defluxity time is the EMF. That's going to be just 2. Ignore the negative because we thought about that already when we talked about directions. L, which is 0.04 over 2 pi times natural log 3. So what voltage is this? What voltage is it not? I don't even know. Okay, so that's 2. Okay, I've got to be doing this wrong. I mean, I don't know. All right, if I'm doing it wrong, say something in the comments. Go, put duck feathers or goose food or something, and then say, by the way, friends, you have a freaking idea what you're doing. Did they tell us the resistance of this? 10. Oh, sweet, merciful crap. What did you make it out of? Ceramic? Sheesh. Okay, so the current is going to be EMF over R, which is 10. So that's going to be 1.75 times 10 to the negative 9. And is this seriously it? This can't be right. That's such a tiny number. Okay, a group of students attempts to experimentally verify whether the current through the light bulb is consistent with the current calculation from part C. Seriously? The current in the rectangular, I must have messed up my flux integral is what I'm pretty sure about, is measured to be greater than the current calculated in part C. Anything's bigger. The current when I sneeze is greater than this. Okay, which of the following could explain this discrepancy? The students did not account for Earth's magnetic field. No, because Earth's magnetic field is constant. Wouldn't have done anything. The rectangular loop is tilted and is not in the same plane as the wire. Well, that's a no because that would result in less flux, less delta flux. The resistance of the light bulb is greater. No, that would result in less current. The long side of the rectangular loop is shorter. That would result in less flux. So no. The current in the long wire changes at a faster rate. Yep, bingo. All right. So since current depends on EMF and EMF depends on defluxity, it's really the same as defluxity time, and flux depends on current, the faster the current changes, the more defluxity time, the more EMF, the more I. Okay. Oh gosh, it's still not going to end. Okay, it looks like everything's the same, but they tilted it that way. Which the following correctly relates the current I2 to I1. I2 is this new case. I1, which is before, this is going to be less. All right, so why is it less? Because now parts of the rectangle are farther away, and the B is less farther away. Okay, right? So magnetic field is less when you're farther away. Okay, so this means there's less flux. So that's going to be less d flux d time. So less EMF, less current. All right. And we're on. Yay! We're at the end of that exam. What's going on here? All right. We've got a solenoid. A solenoid. So this is somebody who eats Domino's pizza by themselves? I don't know. Okay, let's see if we can avoid the solenoid here. A single loop of wire with resistance 3 ohms, radius, placed inside a solenoid. Where do you get such high resistance for a wire? And with the normal, the loop parallel to the axis. 500 turns. Wow, 500. You get around. 0.5 meters long. Is connected to power supply not shown. Time equals 0. The power supply is turned on. I guess Mrs. Power Supply is wearing her nice outfit today. And the current I in the solenoid as a function of time is given by that 5. Okay. At time t equals 0 is the induced current in the loop as seen from the energy clockwise, counterclockwise. Okay, so the I is increasing clockwise. So to oppose that change, there's going to be a counterclockwise current. Okay, I don't think this would get full points, but here's what I'm going to say. I'm going to say Lenz's law says the induced current creates magnetic field opposing the changing magnetic field. Okay, so since I of t increases and creates increasing magnetic field, the induced I is opposite direction to oppose that increasing B. Okay, calculate the current in a loop of wire at time to, wow, seriously? Okay, there's going to be a lot to this. All right, so flux is B times area. Do we have an area for the little loop? Oh, no, we have a tiny radius. Glorious. Okay, so we have a magnetic field. Oh, what is the magnetic field from a solenoid? Mu naught times number of turns per meter. How about I call that number of turns over length? I, mu naught, and I. That's the magnetic field from a solenoid. The area then is going to be pi little r squared. That's the flux. The EMF is going to be the defluxity time. So that's going to be mu naught n over L times the did time, because the I is what's changing. None of this other it's changing with time. Okay, and then I'm going to set that equal to I times resistance. So resistance, which is not as futile as I thought it was. Let's see. DI does not need actual freaking numbers for this crap. Okay, so mu naught, 4 pi, 10 to the negative 7. Number turns 500. Resistance, not futile, it's 3. Length, 0.25. That's a tiny solenoid. It's not something men want to hear if they have a tiny solenoid, okay? My solenoid's big. The DID time is going to be 5, because that's just the derivative of that linear shit. Oh, I got a double pi. This is why me. Okay, so here we go. I'm going to plug this in my calculator. Turn on. Okay, 4 pi e negative 7, 500 over 3 over 0.25 times 5 times pi times 0.1 squared. I didn't mean to do inverse function. Sure, why not? 1.32 10 to the negative 4. All right. 1.32 10 to the negative 4 amps. Okay. Calculate the total energy dissipated by the loop of wire from time 0 to time 2. Okay. So, oh, it's a constant current. So I can just say P equals I squared. I was about to think I was going to take an integral. Oh, I don't have to take an integral. I'm so happy. Okay, so it's going to be 1 point, what the hell did I just say? 3, 2 times 10 to the negative 4 squared times the R. What was the R again? What was the R again? R was 3, okay? So that's 3, so that's power, okay? And then energy is power times time. So the energy then would just be this times 2 seconds. So I just take this and multiply by 6. I get 7.8, 7.9 basically, 10 to the negative 4 joules. A group of students attempts to verify the calculation of the current from part B. The current in the inner circular loop at time t equals 2 seconds measured to be less than the current we thought it would be, which the following could explain this discrepancy. No, the Earth's magnetic field is constant. No, actually, I might come back to that one because it does say less. That could do it. The center of the loop is not on the axis of the solenoid. No, because the magnetic field side of solenoid is basically uniform. The resistance of the loop is less. Nope, that would make more current. The radius is large. Nope. So yeah, this is actually that one right there. So the plane, make mark. It's this one, Mr. Reader. Okay, that one right there. Okay, the plane of the loop is not perpendicular because if the loop is not perpendicular to B, then the flux is less, then the deflux d time is less, then the EMF is less, then the current is less. All right, got to connect all the dots. What the heck? What'd you space it out differently for? Did two completely different people write this page? It's all spaced out. What's with the double space? Did you want to make it look more? Anyway. All right. The power supply is now turned off. Yeah, power supply's mother-in-law called while they were in the middle. Okay, so the original loop of the wire is then replaced, and the second loop is made from a wire that has the same thickness, and it's made from the same material as the original loop of wire. The second loop has, what's the original loop's radius? Has less radius. Okay. The power supply is turned on, and the current in the solenoid is still that. Oh, okay, the power supply is turned on, so they must have gotten back to it then. All right, so which of the following expressions clearly indicate that ratio? Okay, so let me think for a moment. What did I write down before? I had this. Okay, so let me just say that what was I thinking here? The current. Why did I put R here? Did I not mean to put I here? Yeah, that I. That I. Oh, yeah, I guess I meant to put that I here. Okay, well, whatever. I obviously wasn't thinking. Okay, so I was mu naught number of turns over resistance times the length of the solenoid. So these two are the properties of the solenoid. Di dt, that's the rate of change in the solenoid, pi radius of the loop squared. So I'm going to underline things that are properties of the loop. That and that. Everything else is about the solenoid. So none of the rest of that solenoid stuff's going to change. Now, R is resistivity, the length of the loop over the thickness of it. So if I say mu naught n over, here we go, resistivity length over area times the length of the solenoid here, di dt times pi r squared. Now, length is 2 pi r. It's the same thickness. So now what I'm going to do is I'm going to say that this r cancels with that r, and so the I will decrease, and it will decrease linearly. So you only did, how much did you chop it down by? You went from a quarter to 20 cents, so you chopped it down by a fifth. So if you chop it down by a fifth, I2 over I1 would be 0.8, right? It'd be 0.2 over 0.25. So that would be this. Okay, so what am I going to say? I'm going to say the EMF is less by the square of the R's change. The R is less by R to the 1, right? So the I is less by R to the 1, 1 power. R to the 1 power. I don't want that to look like an apostrophe. I want it to look like an exponent. So the I is less. It's just less. All right, so that's the deal there. The high is less. All right, well, I'll post some videos when the P1 and P2 come out, assuming I feel like actually doing them. This is rough. This is how many? This is 12 questions between these two exams. Why? Just stop with the set 1 and set 2. You just basically make the same questions anyway.